Scientists studying Mars have one guiding principle that drives everything they do, a mantra that shapes every mission, every instrument, every rover wheel turn across that rusty, frozen landscape. And that mantra is simply this: follow the water. Think of it like a detective story. When a private investigator in some rain-soaked city wants to untangle a web of crime and corruption, they follow the money, chase the dollar signs, trace the ones and zeros, and eventually, if they're dogged enough, they find their perpetrator. On Mars, the case is far older and far colder. It's one of the greatest unsolved mysteries in the history of human curiosity, one that has baffled thinkers for hundreds, possibly thousands of years. Did life ever arise on Mars? And like any good investigation, cracking that case is all about collecting the right evidence. Here's the key insight that drives the whole search. If water once flowed on Mars, and the evidence is increasingly pointing toward yes, then the sediments left behind by that water could preserve chemical signatures of ancient life. Find the water, and you might just find the fingerprints of something that once lived. It's a simple idea, but the implications are staggering. And the good news? Science has deployed some extraordinary detectives to do exactly this kind of field work. They don't sleep. They don't get tired. Their memories are literally photographic. We're talking, of course, about rovers. Today we're going to walk through some of the most important moments in rover history, the moments when these mechanical explorers cracked the water case wide open on Mars, piece by piece, rock by rock, mineral vein by mineral vein. It's quite the story. Just don't expect a femme fatale. There have been 6 successful rover missions on Mars in total, but for the purposes of this deep dive, we're going to focus on 3 of them: the National Aeronautics and Space Administration's Opportunity rover, the National Aeronautics and Space Administration's Perseverance rover, and China's Zhurong rover. 3 very different machines, 3 very different chapters in the same unfolding investigation. Let's start at the beginning, or rather, the middle, with Opportunity. The date is the 15th of December 2010. 2,449 Martian solar days, called sols, into Opportunity's mission. The rover's primary scientific goal was to find evidence of past oceans on Mars, and by this point, it had already done an enormous amount of legwork. Opportunity had traveled over 25 kilometers across the Martian surface, studying rocks, investigating craters, analyzing bedrock, and navigating across vast sandy plains and wind-sculpted dunes. The clues it had gathered so far strongly suggested that the regions it explored were periodically flooded by water at some point in the ancient past. But there was a crucial distinction the scientists needed to make. Periodic flooding is one thing. A persistent, stable body of water, like a lake or an ocean, is something else entirely, and far more significant for the question of life. Opportunity hadn't yet found the smoking gun. It needed something more definitive. On top of that, Mars's brutal environment had started to take a toll on the rover itself. Some of its onboard motors had begun to fail, which meant Opportunity could no longer stow its robotic arm away properly. Imagine a field geologist who can no longer put their tools back in their pack. They just have to carry them out in front of them constantly. That was Opportunity's situation, but it pressed on. At this point in the mission, Opportunity had just arrived at a feature called Santa Maria Crater, but scientists had their eyes on something far more exciting on the horizon, a massive 22-kilometer-wide crater called Endeavour. And what made Endeavour so compelling wasn't just its size, it was what had been spotted there from orbit. The Mars Reconnaissance Orbiter, a spacecraft circling high above the planet, had detected the presence of clay minerals inside and around Endeavour's rim. Now why does that matter? Because clays are hydrated minerals. They only form in the presence of water, specifically liquid water that sat around long enough, pooled in one place for extended periods of time, and chemically altered the surrounding rock. Clays are, in a very real sense, fossilized evidence of standing water. They're like a geological receipt, proof that water was there and stayed there. After spending 3 relatively quiet months at Santa Maria Crater, Opportunity began making its way toward Endeavour, aiming for the closest section of the crater's rim, a feature known as Cape York. Along the way, it encountered several small craters, some of them geologically very young. You could tell because the material blasted out by the impacts, called ejecta, was still scattered across the surface, not yet buried or worn away by time. But Opportunity didn't linger. As it drew closer to Endeavour, the landscape started to change in ways that must have felt almost dramatic after years of crossing flat, featureless plains. Peaks and elevated ridges, what planetary geologists call capes, began rising up on the horizon. The terrain had personality again. On Sol 2709, Opportunity finally arrived at Cape York, and specifically, it reached a location that the mission team had named Spirit Point, a tribute to Opportunity's twin rover Spirit, which had fallen silent on the opposite side of Mars just a few months earlier after an extraordinary mission of its own. By the time Opportunity reached Spirit Point, it had traveled over 30 kilometers, 50 times further than the distance it was originally designed to cover. Think about that. The mission planners had planned for a rover that would travel roughly the length of a few city blocks. Instead, they got a cross-country expedition. The science team decided not to descend into Endeavour crater itself. Instead, they focused on the rim, where the bedrock was exposed directly at the surface. This was hugely valuable. The rocks around Endeavour's rim were the oldest Opportunity had ever examined, ancient material pushed up by the original impact that formed the crater billions of years ago. And it was precisely along these peaks and capes of the crater's rim where the Mars Reconnaissance Orbiter had detected those hydrated clay minerals. Standing at the top of Spirit Point, Opportunity had a commanding view across the full sweep of Endeavour crater, a perspective that made the sheer scale of the place almost overwhelming. From the very beginning of Opportunity's time around Endeavour, scientists started encountering things they had never seen before anywhere on Mars. One of the strangest early discoveries had actually begun much earlier in the mission: tiny spherical rocks, perfectly smooth and round, scattered across the Martian soil in enormous numbers. The science team nicknamed them blueberries, not because they're blue, but because of their small, round shape. These geological oddities had puzzled researchers for years. Their precise formation mechanism was still being debated, but the leading hypothesis was that they hinted at a watery past, potentially formed through mineral precipitation in water-saturated rock. But here's the interesting thing. Around Endeavour crater, there were no blueberries. None. The soil looked completely different, coarser, grittier, with rocks that were sharper and far less rounded than anything seen at earlier locations. The mission controllers were so struck by how dramatically different this region looked and felt compared to Opportunity's original landing site that they described it as getting a second landing site for the price of one. It was essentially a brand new geological environment, right there on the same planet. The first specific target Opportunity examined at this new location was a large chunk of ejecta, rock thrown out by an ancient impact called Tisdale II. And it was unlike anything previously studied on Mars. It had volcanic characteristics, but its chemical composition was unusual. It contained elevated levels of zinc and bromine compared to other Martian rocks examined before. Analysis revealed it to be a type of rock called breccia, essentially a mixture of older rock fragments that had been fused together by pressure and heat. This alone was interesting, but the really significant part was what it implied about water. The impact that launched Tisdale II into its current position likely also released superheated underground water in the process, and that water appears to have deposited zinc into the rock as it moved through it. Water, acting as a chemical transport vehicle, leaving its calling card in the minerals. But the most conclusive piece of evidence Opportunity found, at least up to that point in the mission, was hiding in plain sight, just a short distance from Tisdale II. In images of a rocky outcrop, there is a thin, bright white line cutting through the darker surrounding rock, just a sliver of something different. A close-up examination using the alpha particle X-ray spectrometer, an instrument mounted on the rover's robotic arm that can identify the elemental composition of a rock surface, revealed that white line to be gypsum, specifically calcium sulfate. The minerals calcium and sulfur were both present, combined in a form that only makes sense in the context of water chemistry. The science team named this feature the Homestake deposit. Here's what they believe happened. Ancient water dissolved calcium out of surrounding volcanic rocks. That calcium-rich water then combined with sulfur and was carried deep underground, flowing through fractures in the bedrock. Over time, as conditions changed, that calcium sulfate precipitated out of the water and was deposited inside those underground fractures, essentially filling the cracks with mineral cement. Eventually, erosion exposed those cracks at the surface, revealing the white vein we can see today. The impact that threw Tisdale 2 was likely connected to this process as well, possibly creating or opening the fractures that the water then flowed through. What makes the Homestake deposit especially exciting isn't just that it's evidence of water. It's evidence of a particular kind of water. Later analysis of the data Opportunity collected showed that the water which formed this gypsum vein was significantly less acidic than the water thought to have existed at other locations on Mars. And that's enormously important. Highly acidic water is hostile to life as we know it. Less acidic water, water closer to neutral on the chemical scale, is far more conducive to the kind of chemistry that life depends on. In other words, the water that flowed through Homestake wasn't just water. It was potentially the right kind of water for life. As the scientific excitement around these discoveries was building, Martian winter began to close in. The days grew shorter, the sun dropped lower in the sky, and for a solar-powered rover that cannot tilt or reposition its solar panels to track the sun, that's a serious operational problem. Less sunlight means less power, and less power means the rover has to be parked somewhere safe and strategic to wait out the season. But for the first time since the mission began, Opportunity found itself in exactly the right spot at exactly the right time. There was a slope available, one that faced toward the sun, that would allow the rover to maximize its solar energy intake throughout the winter months. The team set Opportunity up at this location, a site they named Greeley Haven. Greeley Haven turned out to be more than just a convenient parking spot. The area was rocky and geologically interesting, giving Opportunity plenty to study during the long winter months. The rover captured a stunning 360-degree panoramic image showing its own tracks in the Martian soil, winding across the landscape as it carefully maneuvered into its winter position, a kind of portrait of a machine settling in for the cold. Months passed. Winter gave way to spring and then to summer. On Sol 2947, Opportunity moved again for the first time since making camp at Greeley Haven. So when Opportunity woke back up after that harrowing dust storm, the mission team breathed a collective sigh of relief. Everything that had been working before was still working. And with that reassurance, Opportunity pointed itself toward the next point of interest. Data from the Mars Reconnaissance Orbiter, a spacecraft that had been imaging the Martian surface from orbit, suggested that clay minerals were present in this part of the region. Clays are incredibly significant because they almost always form in the presence of water, and the mission team were absolutely determined to find them. Around Sol 3057, remember a Sol is a single Martian day, just slightly longer than one of ours, Opportunity's cameras picked out a compelling outcrop of rock. Scientists directed the rover's microscopic imager toward it, and what came back was something nobody had anticipated. The surface of the rock was studded with small, smooth, rounded formations, strikingly similar to what had been nicknamed the blueberries way back at Opportunity's original landing site. But here was the twist. This time, these little spheres weren't loose and scattered across the ground. They were embedded directly into the rock itself, like blueberries baked right into a muffin rather than sprinkled on top. And these new blueberries were different in other important ways too. They were noticeably smaller than the ones Opportunity had encountered at its landing site, only a few millimeters across. And crucially, they weren't rich in iron the way the original blueberries had been. A handful of them had been partially eroded away, which was actually a stroke of luck for scientists, because it exposed their internal structure for study. What researchers found was fascinating. They described these formations as, and this is a direct quote, crunchy on the outside and softer in the middle. They were different in concentration, different in structure, different in composition, and different in distribution from anything Opportunity had previously encountered. Nobody had a clean explanation for them. It was quite the mystery, and one that added yet another layer of intrigue to Mars's complex geological story. Now, Opportunity had just one more stop on its tour of the Cape York Ridge, and that was a clay-rich patch the team had nicknamed Whitewater Lake. But getting there involved a bit of an unplanned drama. As Opportunity was making its way across the Martian surface, Earth and Mars entered a phase called solar conjunction. This is a predictable event that happens periodically, where Mars moves to a position directly behind the Sun from our perspective, which means the Sun itself physically blocks any radio signals trying to travel between the rover and its controllers back on Earth. Communication goes dark. It had happened a number of times already during Opportunity's long mission, so in principle, the team knew what to expect. But this time, during the blackout, Opportunity's onboard computer unexpectedly reset itself and dropped into standby mode. That was a tense moment. Thankfully, once the conjunction passed and communications were restored, Opportunity booted back up correctly and resumed its journey toward Whitewater Lake without any lasting damage. And it was there, at Whitewater Lake, that Opportunity found what would become one of the most significant rocks of its entire mission. It was a pale-colored rock sitting in the upper center of one of the rover's camera images, roughly the size of a human forearm. Scientists named it Esperance. And this was the treasure they had been hunting for. Analysis revealed that Esperance had a chemical composition unlike anything Opportunity had tested in more than 9 Earth years of roving. It was higher in aluminium and silica and lower in calcium and iron than any other rock the rover had examined. When scientists dug into the data, they found clear evidence that the rock contained clay minerals that had formed through extensive alteration by water. Not a brief splash of water, but prolonged, intensive contact. Opportunity spent weeks at the Esperance site, methodically taking measurements and double-checking its results, making sure the data was solid and complete before the Martian winter closed in again and forced the team to limit the rover's activity. Opportunity finally departed Cape York on Sol 3344. By that point, it had spent 9 Earth years on the Martian surface, or equivalently 5 full Martian years. And over that extraordinary span of time, it had delivered what scientists described as the strongest evidence of any Mars mission to date that neutral pH water, not acidic, not highly alkaline, but genuinely hospitable water had once existed on Mars. That's the kind of water that life as we know it could actually thrive in. But of course, scientists are never fully content to stop at one answer. Knowing that water once existed somewhere on Mars is one thing. Understanding where water was most abundant, where it lingered longest, and where life might therefore have had the best chance of taking hold, that requires exploring more locations. So in the year 2021, humanity's next rover was dispatched to a completely different region of the planet, a massive impact crater called Zhurong, located thousands of kilometers from where Opportunity had been working. Now, Zhurong crater is a genuinely spectacular place. Scientists have long believed it was once home to an ancient lake fed by a river delta, similar in some ways to river deltas here on Earth, like the Nile Delta or the Mississippi Delta, where sediment builds up over vast stretches of time. Within Zhurong, there is a large dune field known as Zhurong, and tucked among those dunes are a series of rocky outcroppings, places where erosion has stripped away the upper layers of the surface and exposed the geological record beneath. These outcroppings were of enormous interest to the Perseverance rover's science team because each distinct layer of exposed rock likely represents a different chapter in Zhurong's history, a different geological era, frozen in stone. Reading those layers, scientists believed, could give them the clearest possible picture of what this crater looked like billions of years ago and whether conditions for life ever existed here. Here's why outcroppings matter so much. Perseverance's coring drill, its primary tool for collecting rock samples, can only penetrate several centimeters into the ground. That's not very deep. If you want to study what's happening meters below the current surface, you're essentially out of luck, unless erosion has already done the work for you and brought those deep layers up to where the rover can reach them. Outcroppings are, in a sense, nature's shortcut through time. But getting to those outcroppings meant crossing the sand dunes of Zeta, and that introduced a serious hazard. Sand dunes might not sound particularly threatening, but for a rover operating on a planet where the nearest repair crew is tens of millions of kilometers away, they can be mission-ending. Back in 2009, the Spirit rover, Opportunity's twin, became fatally stuck in a patch of loose Martian soil. Its wheels spun without traction, it couldn't free itself, and eventually the mission was lost. The Perseverance team had absolutely no desire to repeat that outcome. This is where Ingenuity entered the picture. Ingenuity is a small helicopter, a genuinely revolutionary piece of technology, and the first rotorcraft ever to fly on another planet. It had made the journey to Mars tucked beneath Perseverance's belly, and had already demonstrated that powered flight was possible in the thin Martian atmosphere. Now, it was given a new and vital job: reconnaissance. Ingenuity would fly ahead of Perseverance into the dune field, scout the terrain from the air, and try to identify a safe route through to the outcroppings. Ingenuity began its scouting flights before the next solar conjunction and continued flying from September through to December of 2021, conducting multiple flights at a height of 10 meters above the Martian surface. From up there, its cameras could pick out subtle features of the dune terrain that the ground-level view from Perseverance simply couldn't reveal. Patches of firmer ground, routes between the dunes where the sand was less likely to swallow a wheel. Those aerial surveys allowed scientists to map out a path that looked genuinely safe. Perseverance set off in early November of 2021. It moved carefully and deliberately, picking its way between dunes that rose about a meter off the ground, always choosing the flattest available path, never pushing its speed to the point where it might suddenly find itself sinking into a hidden sand trap. And Ingenuity's reconnaissance proved its worth completely. Perseverance navigated the dune field successfully and arrived at a protruding rock formation called Brack, its gateway into the geological archive of Zeta. By this point, Perseverance had had some time to practice its coring technique on other Martian rocks. Some attempts had gone well, others less so, but the team had refined their approach, and at Brack, the rover was able to obtain fresh samples efficiently. The first sample container used at this location was designated an atmosphere sample, capturing Martian air rather than rock. The next two samples collected became Perseverance's fifth and sixth overall sample tubes, and its third and fourth rock cores. And what those cores revealed was a genuine surprise. Scientists had gone into Zeta expecting sedimentary rock, the kind of rock formed when layers of sand, silt, and other particles slowly accumulate and compact over time, often at the bottom of a lake or river. Sedimentary rocks are the classic targets in the search for ancient life because they can preserve biological material. But that's not what Perseverance found. Instead, the samples contained igneous rock, specifically a mineral called olivine. Olivine is actually a rock type you can find here on Earth. Parts of Australia have olivine-bearing formations, and it's also commonly found in volcanic regions around the world. The defining feature of igneous rock is how it forms, not from settling particles, but from molten magma cooling and solidifying. Finding olivine in Zhurong crater told scientists something important about the crater's deep past, that at some point, this location had experienced volcanic activity. Now, at first glance, that might sound like disappointing news. Magma is not exactly a hospitable environment for life. But here's where the story gets more interesting. The rocks didn't just show signs of volcanic origin, they also bore clear marks of water erosion. The ridges running along the edges of the crater showed features consistent with water having flowed through here. And the famous delta structure at Zhurong, that ancient river delta that made the crater so scientifically compelling in the first place, must have formed after the volcanic activity had already concluded and the rock had cooled. So the sequence would have been something like this: volcanic eruptions, cooling and solidification, and then water. And that order of events is actually very good news for the search for life. Igneous rock tends to be extraordinarily mineral rich. Think about why the soil around volcanoes here on Earth is so incredibly fertile. Places like the slopes of Mount Etna in Sicily or the volcanic highlands of Hawaii are among the most productive agricultural regions in the world. Minerals pour out of magma as it cools and weather into the surrounding environment. So if you combine that mineral richness with the presence of liquid water flowing over and through those rocks afterward, you've got something that looks a lot like the conditions that life needs to get started. In the years ahead, missions targeting locations like the Zhurong crater delta could yield extraordinary findings as scientists continue the search for signs of ancient alien life. And looking further into the future, toward the 1930s, when crewed missions to Mars are being planned, it's genuinely conceivable that sites like this one could become the locations of the first archaeological excavations on another planet. Picture astronauts in pressure suits gently brushing away the fine reddish dust, that oxidized iron and basalt powder that gives Mars its characteristic color, to see what might be preserved in the layers beneath. So we've established that water almost certainly pooled in craters and carved out rivers across ancient Mars. But what about going one step further, one giant leap further? Could ancient Mars have once had actual oceans? Full-scale, coastline and all oceans? If that turns out to be true, it's enormous news for anyone searching for signs of ancient alien life. Because a shoreline isn't just a pretty place to visit, it's essentially a life support system. Coastlines can sustain entire diverse ecosystems, packed with organisms taking advantage of everything the environment has to offer. And if life ever existed along a Martian coast, it may have left behind what scientists call biosignatures, chemical and physical clues baked into the rock, like a cosmic scavenger hunt that could help us paint a detailed picture of what Mars's ancient coastal habitats were actually like. Here's why shoreline environments are so special when it comes to the origin of life. First, they concentrate organic molecules through evaporation. Think of it like a natural chemistry lab where the ingredients keep getting more and more concentrated over time. Second, they promote the formation of complex molecules like ribonucleic acid and protein, the very building blocks of life as we know it. Third, they offer mineral-rich surfaces along with a whole menu of energy sources. Ultraviolet radiation from the sun, heat, and chemical gradients, all of which can drive the kinds of reactions needed to kickstart life. Rivers, by contrast, just don't have the right conditions. They're too dynamic, too dilute. Water rushing downstream constantly flushes materials away before molecules ever get a chance to accumulate and react. It's like trying to bake a cake in the middle of a waterfall. So while rivers are great evidence of a wetter past, they're not ideal nurseries for life. This is why finding evidence of a standing body of water, a lake, and especially an ocean, is such a big deal. That kind of environment gives researchers a much more promising target in the search for remnants of ancient microbial life. And it turns out, the Chinese Tianwen-1 mission may have just delivered the most compelling evidence yet that ancient oceans really did exist on Mars. What makes this especially remarkable is that it's the first time anyone has collected on-the-ground data from a suspected ancient ocean zone. This isn't satellite imagery or theoretical modeling. This is data gathered right there, on the surface. And it makes a very strong case that the ocean shoreline theory is pointing us in the right direction. Let's talk about the mission itself. On the 23rd of July 2020, the Tianwen-1 spacecraft launched from Earth and began a 202-day journey to Mars. The spacecraft carried 3 components: an orbiter, a lander, and a rover named Zhurong. The mission had 3 main objectives. First, to study the surface and subsurface of a region called Utopia Planitia, a place scientists had long suspected might be an ancient ocean basin based on satellite mapping data. Second, to monitor Mars's climate and weather, including variations in the magnetic field and the effects of dust activity on solar panels and atmospheric conditions. And third, to search for signs of water and habitability, essentially asking whether this region ever had the right conditions to support life. On the 10th of February 2021, Tianwen-1 entered orbit around Mars. Controllers spent 3 months carefully testing the spacecraft's systems, shifting its orbital path from equatorial to polar, and getting everything ready for the main science mission. Then, on the 14th of May, the lander touched down on the red planet. A week later, the Zhurong rover rolled out onto Martian soil, making China only the second nation in history to successfully operate a rover on Mars, after the United States of America. For China, this mission meant far more than just scientific discovery. It was a statement. It demonstrated the country's spaceflight capabilities and technological independence, proving that China can design, launch, and operate deep space missions entirely without relying on foreign navigation or communication infrastructure. The name Tianwen, which translates to something like "questions to heaven," was chosen deliberately, and the mission was designed to lay the groundwork for even more ambitious future projects, including a Mars sample return mission and a possible crewed mission to Mars as early as 2033. The Zhurong rover itself weighed 240 kilograms, roughly the weight of a large adult male polar bear for reference. It was deployed in Utopia Planitia, which holds the distinction of being the largest known impact basin in the entire solar system. Interestingly, this is the same region where NASA's Viking missions landed almost 50 years ago. But scientific interest in the area got a serious revival in 2016 when NASA announced a major discovery. Utopia Planitia is home to a staggering amount of underground ice. We're talking about roughly as much water as you'd find in Lake Superior, approximately 12,100 cubic kilometers, or around 10 to the power of 16 liters. That is an almost incomprehensible amount of water hiding just beneath the surface. To study this region properly, the Zhurong rover came equipped with 13 different scientific instruments, which can be grouped into 4 broad categories. First, ground-penetrating radars capable of detecting subsurface structures up to 100 meters underground, including the rover's headline instrument, the rover radar. Second, spectrometers for analyzing the chemical composition of soils and rocks, including a laser-induced breakdown spectrometer and an infrared spectrometer. Third, optical cameras mounted on both the orbiter and the rover, used for imaging the planet's surface, mapping topography, and providing navigation capability. And fourth, atmospheric and space environment monitors, including a surface magnetometer and the Mars Climate Station, a suite of instruments designed to track local temperature, wind speed, atmospheric pressure, and even record sound on the Martian surface. The rover also carried a deployable wireless camera, essentially a selfie camera, that it could drop onto the ground and photograph itself with. It produced some of the most iconic images of the entire mission. So with all of that scientific firepower on board, what exactly did Zhurong discover about the Martian coastline that previous missions had completely missed? To understand the discovery, we need a quick geography lesson. Bear with me because this is where things get really interesting. On Earth, sediment, the tiny particles of sand, silt, and rock, gets transported by wind, water, and ice. Rivers carry it downstream, glaciers drag it across the landscape, and eventually it gets deposited in calm, low-energy environments, river deltas, lake floors, ocean beds, floodplains, the bases of mountains. But sediment also accumulates along coastlines, and specifically in the zone known as the foreshore, the stretch of beach between the high tide line and the low tide line. This is a dynamic, constantly changing zone where sediment is both added and removed depending on wind, tides, weather, and the size and type of particles involved. One key feature of foreshore zones on Earth is that they tend to slope gently toward the sea. The steepness of that slope depends on what the beach is made of. Fine-grained sandy beaches produce a gentle, shallow gradient, but beaches covered in cobblestones can be stacked as steeply as 20 degrees. These sloping sediment layers are essentially a geological record. They capture the long-term balance between sediment supply, wave energy, and water level. And crucially, they can be preserved in the rock record for millions, even hundreds of millions of years. Now, back on Mars. The Zhurong rover was busy studying the planet's subsurface using its rover radar. The way this works is beautifully straightforward. The instrument sends radio waves down into the ground, and when those waves hit a boundary between two different materials, say where fine-grained sediment meets coarser sand, some of the signal bounces back up to the rover. Each one of those bounce backs shows up in the radar image as what scientists call a reflector. What caught the Zhurong team's attention wasn't just that signals were bouncing back, it was the angle at which they were bouncing. All 76 of the geological reflectors they detected were sloping in the same direction, at angles ranging between 6 and 20 degrees. When the team assembled the full picture, they realized that somewhere between 10 and 35 meters below the Martian surface, there is a 1.3-kilometer stretch of terrain sloping consistently toward the lowlands. That is not a random geological coincidence. That looks remarkably like a buried ancient beach. The team immediately began comparing this Martian subsurface picture to buried beaches found here on Earth, and the match they found was striking enough to feature it directly in their published research paper, the Bay of Bengal. The geometry, the slope angles, the layering, it all lined up with extraordinary similarity. One of the co-authors of the research paper put it perfectly. They said, and I'm quoting here, "It's a simple structure, but it tells you there had to be waves, there had to be a nearby river supplying sediment, and all these things had to be active for some extended period of time." Think about what that means. Waves require an open body of water, a river supplying sediment requires a sustained hydrological system, and the fact that those layers are preserved and sloping in a consistent direction means this wasn't a one-time flash flood. This was a stable environment, possibly over a very long period. And here's something fascinating. Both the Sun and Phobos, the larger of Mars's two moons, actually do exert a measurable pull on the planet's surface gravity. That gravitational influence would have been enough to drive tides on an ancient Martian ocean, much the way the moon drives tides here on Earth today. Now, the research team didn't just jump straight to the ocean conclusion. They carefully considered other possible explanations for those sloping underground structures. Could they be sand dunes? Could they be ancient lava flows? Both of those were seriously considered, and both were ruled out. Here's why. Sand dunes and lava flows tend to pile up and spread in all sorts of directions depending on local conditions. You'd expect to see slopes pointing every which way, but that's not what the Zhurong radar data showed. Every single one of those reflective slopes pointed in the same direction. That kind of consistency is a powerful fingerprint. The team concluded that what they were looking at was most consistent with a coastal foreshore environment, the kind of sloping, layered terrain you'd get where a shoreline meets the sea. This adds serious weight to the idea that Mars once had dynamic, living coastlines, places where tides rolled in and out, where wind whipped across the water, and where waves shaped the land, just like the beaches and shores we know here on Earth. Now, as exciting as all of that is, it brings us face to face with one of the biggest and most stubborn puzzles in planetary science. Scientists have been wrestling with this one for decades, and it doesn't have a clean answer yet. It's called the faint young sun paradox. Here's the core of the problem. 3.5 billion years ago, our sun was roughly 25% dimmer than it is today. That might not sound like much, but in terms of planetary climate, it's enormous. A sun that faint simply should not have been able to keep Mars warm enough for liquid water. The temperature should have been well below freezing across the entire planet. And yet, when we look at the geological record, we see rivers, we see lake beds, we see what looks very much like ocean shorelines. Our climate models keep telling us Mars should have been covered in flowing water, even while the physics of a dim young sun say that shouldn't be possible. That contradiction is the paradox. If the warmth didn't come from sunlight, it had to come from somewhere else, and the most obvious candidate is the atmosphere. Scientists have come up with 3 broad theories to try to crack this puzzle, and each one has genuine strengths and genuine problems. The first theory says Mars was warm and wet, more or less continuously, for a long stretch of its early history. The idea here is that Mars had a thick, heavy atmosphere packed with greenhouse gases, primarily carbon dioxide and water vapor. Think of it like wrapping the planet in a very effective thermal blanket. Dense enough, and that atmosphere could trap enough heat to keep liquid water stable at the surface for millions of years. This would explain the rainfall signatures, the lake deposits, and the apparent oceans. The trouble is, when you actually run the numbers, carbon dioxide and water vapor alone don't produce enough warming to make this work. You'd need other gases, things like methane, ammonia, or hydrogen, to push the temperatures high enough. And those gases are chemically unstable. They break down relatively quickly and are difficult to maintain in large quantities over geological timescales. So this theory is appealing but incomplete. The second theory takes a more episodic view. Maybe Mars wasn't warm and wet all the time. Maybe it was only warm and wet some of the time in response to dramatic, violent events. A massive volcanic eruption, for instance, could blast enormous quantities of greenhouse gases and heat into the atmosphere all at once. A large asteroid impact could do something similar, releasing tremendous energy and temporarily warming the climate. During these short-lived warm spells, ice would melt, rivers would flow, erosion would carve valleys, and lakes would fill up. Then, as the heating faded, the planet would freeze over again until the next big event. It's a compelling idea, but the problem is one of scale. We'd need to know whether these events were frequent enough and powerful enough to account for all the valley networks, lake basins, and coastal features we actually observe. And right now, we don't have a definitive answer to that. The third theory is perhaps the most dramatic. It suggests Mars spent the majority of its history as a frozen world, a giant ice ball basically. Glaciers and ice sheets dominated the landscape. But periodically, something would shift. A change in Mars's orbital path around the Sun, or one of those sudden heating events, and the ice would melt, unleashing floods and rivers and temporarily filling basins with water. This scenario fits neatly with the geological evidence of both glacial features and water erosion that we see on Mars today. The challenge here is explaining what could trigger those melt events often enough and powerfully enough to produce the scale of erosion we're looking at. None of these three scenarios is a perfect fit. Each one explains some of the evidence while leaving other pieces awkwardly unaccounted for. And frustratingly, even though the case for ancient Martian shorelines keeps getting stronger, we still haven't cracked the climate model problem. We still don't fully understand how to make early Mars warm enough and wet enough for long enough. That said, a paper published in the journal Communications, Earth and Environment in December of 2025 offered an intriguing new data point. Scientists analyzing data from NASA's Perseverance rover found evidence that certain clay minerals it encountered had been shaped by consistent, heavy rainfall, not just occasional drips, but sustained precipitation over time. That finding lends support to the warmer, wetter end of the spectrum. But solving the faint young sun paradox completely may ultimately be the key that unlocks the answer to one of humanity's deepest questions. Was Mars ever truly capable of supporting life? So where does that leave us? Well, it means we need more data. The picture is tantalizing but incomplete. In what has been a genuinely heartbreaking development for planetary scientists, Perseverance spent a significant portion of its mission on Mars carefully collecting and caching rock and soil samples, with the plan being that a dedicated sample return mission would launch sometime in 2027 or 2028 and bring those samples back to Earth for analysis by the late 2030s. Those samples could have given us the most detailed look yet at Mars's ancient geology and perhaps settled the ocean debate once and for all. But then came the budget crisis. In 2025, NASA faced the threat of massive funding cuts. Congress did pass legislation in early 2026 that protected most of NASA's budget, but the Mars sample return mission was carved out as the one exception. It did not receive protected funding. What that means in practice is deeply frustrating. Those carefully collected samples, including one that NASA itself described as the clearest sign of life ever identified on the red planet, are sitting on the surface of a world that is, depending on where we are in our respective orbits, tens of millions of kilometers away. They may sit there for a very long time. It is now possible that the only people who will ever walk over and pick them up are future human settlers on Mars, if and when that day ever comes. And what about Zhurong itself? The rover was originally designed to operate for 93 Earth days. It well and truly exceeded that expectation, collecting science data for an impressive 358 Earth days before finally entering a dormant state on the 20th of May 2022. Scientists anticipated that the right combination of temperature and sunlight in December of 2022 would wake it back up, but it never revived. Excess dust had accumulated on its solar panels, starving it of the power it needed to restart. But the questions Zhurong helped raise are very much alive. If Mars really did support stable oceans for millions of years, what happened to all that water? Where did it go? How does a planet go from being a potentially warm, wet, possibly habitable world to the barren, frozen desert we see today? Could the same kind of planetary transformation happen to Earth one day? And perhaps most provocatively of all, if life did somehow emerge in those ancient Martian coastal environments, in those tidal zones where chemistry gets complicated and interesting, could traces of it still exist somewhere, preserved and buried beneath the surface, waiting? Zhurong and the instruments it carried may have given scientists a way to follow the water, but the question of whether life itself once stirred on Mars, that remains a case very much open for investigation.